Alright, hello everybody, and today we're going to be solving this integral right here, the improper integral from negative infinity to infinity of sine of x over x. So I've actually already evaluated this integral in a previous video using Laplace transforms, and today we're going to be doing it using complex analysis. So let's just get started here. Let's take a look at the integrand. Notice that sine of x is an odd function, and x down here is also an odd function. And whenever you have an odd function divided by another odd function, that's just an even function. So the integrand altogether is an even function. And since we're integrating across symmetrical bounds, we can actually split this interval up a little bit and multiply everything by 2. So since this thing here is symmetric, it's an even function, we can say that it's twice the integral from 0 to infinity of the same integrand, sine of x over x dx. So now what can we do with this thing right here? Let's how about introduce a new complex function. Let's call it f of z. And we're going to take the usual approach to this. We're going to replace a sine of x with e to the iz and x with z like so. And we want to integrate this thing right here over a contour and try to force out an integral that looks like this somehow. So let's construct for ourselves a little contour right here. Notice that we have a z on the denominator of this function right here. That means we're going to have a singularity at 0, so the origin right here. So I will just mark that in red. So we want to use a semicircular contour, but we want to avoid this singularity right here. So what we can do, we're going to start off at negative r right here, and we're going to walk along our real axis like so in this direction. But we want to avoid this singularity, so why not take a little detour and take a path over the top of the singularity, and that little semicircle will have some radius of epsilon. So we're going to go from minus epsilon to epsilon, and later we're going to let our epsilon approach 0. So let's call this little semicircle here little gamma like so, and then we're going to continue along our real axis, so volts here. We're going to keep going here, and then we're going to hit some point r like so. And you can kind of see how this path right here from minus r all the way up to r resembles our original interval right here. So to close the contour right here, we're going to construct for ourselves another semicircle which goes from positive r to negative r, so something like that. And we're going to hold this path right here big gamma, and we're going to call our contour c like so. Alright, so now we've got our path figured out for our contour. So that means our contour integral over c of f of z dz, we can decompose it into each of these singular paths right here. So first of all, going from negative r to minus epsilon, so from minus r to minus epsilon of f of x, we're going to replace z's with x's because we're walking across the real number line. And then we're going to add the integral over gamma right here, so little gamma of f of z dz. And then we're going to add the integral from epsilon to r of f of x dx. And then finally, we're going to add the integral over big gamma here of f of z dz. So this thing right here is our expression for our contour integral. And notice one thing about this function right here. This function is completely analytic except for at the point 0 right here. So since we're integrating over a closed contour over an analytic domain, so no point in the interior of our contour is a singularity. So pretty much the value of our contour here is exactly 0. So that's just Cauchy's integral theorem right there. So that means when we add all of these separate integrals up, we need to have it equal to 0. So we've dealt with our contour right here. Let's focus on each of these little integrals right here. So what I'm going to focus on first is this integral as well as this integral. So I'm going to write this integral here first. So we're going to have the integral from epsilon to r of f of x dx, and then we're going to add it with this integral right here, integral from minus r to minus epsilon of f of x dx. So we're dealing with these two integrals right here. So what is f of x right here? Well, let's just use the definition of our function right here. That's the integral from epsilon to r of e to the ix over x dx plus the integral from minus r to minus epsilon of e to the ix over x dx. Okay, and what can we do with this thing right here? Notice that the bounds right here are almost the same. The bounds of this integral just have these negatives right here, which we would like to get rid of, and also the order is kind of messed up. So why not introduce a little substitution? Why not let on this integral u be equal to negative x? So that means that du is equal to negative dx. Alright, and if we do the substitution on this integral, what are we going to get? Well, pretty much we're turning all of our x's here into negative u's. So this x down here will become a negative u, dx will become negative du, so times negative du. Our x at the top here will become minus u, so we're going to have e to the minus I times u, and then we're going to get rid of these negatives right here on these bounds. Alright, and what can we do from here? Well, what I'm going to do with both of these negatives right here, one of them I'm going to bring out to the front right here, so we're going to have a negative integral, and with this negative in front of the du right here, I'm going to use that to switch the order of the integration. So now instead of going from r to epsilon, we're going to epsilon to r, so just switching the bounds around. And notice that u is just a dummy variable. Whatever this integral evaluates to, it's going to be independent of u. So it actually doesn't matter what variable we use right here. So in fact, we can switch our u's back to x's. And you see, now we've returned to our x's here. And for both of these integrals, we have the same bounds. So from epsilon to r. So what that means is we can bring both of these integrands together. And what are we going to get? We're going to get the integral from epsilon to r of e to the ix minus e to the minus ix over x, and then dx like so. And notice that this almost looks like the complex definition of the sine function. All that we're missing down here is a 2i, so why not multiply a 2i on the denominator here and also out here. And what happens now is that this whole entire part right here, that's just sine of x. So now we're going to get 2i times the integral from epsilon to r of sine of x over x dx, and that's really nice because this is the function that we originally wanted. And later we're going to be taking the limit as r approaches infinity and epsilon approaches 0 on all of these integrals. So if we just do it now, so letting r approach infinity and epsilon approach 0, we're going to get 2i times the integral from 0 to infinity of sine of x over x times dx. Alright, so this integral right here will be the value of these two integrals here in the limit as epsilon approaches 0 and r approaches infinity. Alright, so now we're going to deal with the next integral. Let's take a look at this integral right here over little gamma. So we're going to be taking a look at the integral over little gamma of f of z dz. Alright, what exactly is that? That's the integral over gamma of e to the I z over z dz. And what we want to do with this integral is we want to introduce a new parameterization. So we're going to let some gamma of t be equal to epsilon times e to the I pi minus t, where t goes from 0 to pi. And the reason why this parameterization works is because we want to rotate around the origin a little bit. And the radius of our gamma semicircle right here is exactly epsilon. So this makes sure that the magnitude of every single point on that little gamma there is exactly epsilon. And here we have pi minus t. And the reason for that is because we're traversing this path in a clockwise direction. So usually if we go around anti-clockwise, we can just have a t right here. But because we're going anti-clockwise, we need a pi minus t. And this makes sense because if you plug 0 into this t right here, we're going to start at epsilon e to the I pi, which is exactly this point right here. And ending at pi, we're going to have pi minus pi, which is 0. So we're just going to have epsilon, which is exactly this point right here. So indeed, this parameterization works right here. So let's figure out the derivative of gamma. So I'll just write gamma dot of t. That's going to be exactly negative I epsilon e to the I pi minus t. And just using the chain rule, outside derivative e to the something is still e to the something, and inside derivative we're going to have I times minus t right here. So derivative of that is exactly minus I out here. So plugging the parameterization into our original integral right here, we're going to get the integral from 0 to pi now. So 0 to pi of e to the I gamma of t over gamma of t, so replacing all the z's with the gammas of t's right here. And notice one thing here, gamma dot of t, it's also exactly negative I times the original gamma of t itself. So we have negative I times gamma of t. So writing that in, we're going to get negative I gamma of t for our gamma dot, and then we're going to end it off with a dt. So that's just a definition of the parameterization. And the cool thing is this part and this part will cancel each other out. We're going to get a negative I out to the front. So what are we going to get? We're going to get negative I integral from 0 to pi of e to the I gamma of t is exactly this junk right here. So epsilon e to the I pi minus t dt. And remember, we wanted our epsilon in the limit to approach 0. And if we have the integral in this form right here, we can clearly see what happens as our epsilon gets smaller and smaller and smaller. This whole entire term at the top here, that's just going to go towards 0, so it's just going to vanish. And if you have e to the 0, that's exactly 1. So in the limit, as our epsilon goes to 0, we're going to have a negative I times integral from 0 to pi of dt, and that's exactly minus I times pi. So minus I times pi is the value of our integral over little gamma in the limit as our epsilon approaches 0. So let's just add that to our final expression right here. So we've gotten our two integrals we just evaluated. So our integral over little gamma, it's going to be minus I times pi. So just put it like that. And now the last integral to evaluate is this integral over big gamma right here. And for this integral, we can actually use Jordan's lemma on it to show that it's equal to 0. But I'm going to prove it properly in this video that this does indeed go to 0. So now let's calculate the integral over gamma of f of z dz. Again, like our integral over little gamma, we need to introduce a new parametrization. So this integral, that's the integral over gamma of e to the I z over z dz. So let's just choose some new function. Let's call it phi of t to be equal to capital R times e to the I t, where t is between 0 and pi. So we're going around the origin right here. So we want to have e to the I t, and we're going anti-clockwise as well. So this works right here, and the modulus of every single point z on our gamma right here is exactly R. So this parameterization works. So we're going to have phi dot of t to be equal to I times R e to the it, and similar to before, we can say that that's exactly I times our original phi of t, like so. So plugging all of this information into here, we're going to get that it's equal to the integral from 0 to pi of e to the I phi of t over phi of t, and then we need a phi dot of t here, but that's exactly I times phi of t, and then dt to end it off. Alright, these two parts right here will cancel each other out, and we're going to be left with I times the integral from 0 to pi of e to the I phi of t is R times e to the it dt. Alright, so once we've parameterized this integral right here, we need to estimate its value as our R here approaches infinity. Alright, so to estimate this integral right here, we can just use the estimation lemma. So just taking the absolute value of I times the integral from 0 to pi of e to the I reit dt. And since we're multiplying two things right here, we can split the absolute value up, but the absolute value of I is exactly 1, so let's just get rid of that. And now what can we do from here? Well, let's expand out this e to the it right up here. So this is exactly absolute value of the integral from 0 to pi of e to the ir cosine of t plus I times the sine of t. So just using Euler's formula right here. And from here, what we can do is expand out this bracket right here and split up the exponential. So we're going to have absolute value integral from 0 to pi of e to the I r cosine of t, and then I and I is negative 1, so we're going to have e to the minus r sine of t, like so, dt. And then using the integral inequality, we can say that this thing right here is less than or equal to the integral of the absolute value, so integral from 0 to pi, and then putting the absolute value inside of the integrand right here. But since we're multiplying two things, we can split the absolute values up. So we're going to have absolute value e to the I r cosine of t, and then e to the minus r sine of t, like so, dt. And the cool thing is e to the I times some real number right here, because r is a real number, cosine of t is a real number because t is a real parameter. So if we have e to the I times some real number, the modulus of that is actually always equal to 1, because on the unit circle, every single point is exactly 1 unit away from the origin. So this thing evaluates to 1, and then we have this part left. So e to the minus r sine of t. R times sine of t is a real number. And if you have e to any real number, that's actually always greater than 0. So we can actually ignore the absolute values on this part right here. So now we're going to have the integral from 0 to pi of e to the minus r sine of t dt. And here you can kind of see that as we let our r here approach infinity, this whole thing's going to go to 0. But before we do that, we need to look at something a bit technical, because if you look on our interval of integration, we're going from 0 to pi. And if you plug a 0 into this t here, as well as pi into this t, we're going to get 0 right here, and e to the minus 0 is always 1. So the problem with this integral is that we're going to get 1 if our t is equal to 0 or pi, and 0 for anything else in between. So if we restrict our interval of integration to 0 to pi, but not including these endpoints right here, our integral will actually go towards 0. So our integral is the same whether we integrate across this interval or this interval, and we're going to choose this interval right here because then we don't have to worry about our upper bounds of our integral being 1. So with that out of the way, as our r approaches infinity, this thing right here will approach the integral from 0 to pi of 0 dt, which is of course just 0. So what did we just find out right here? Our integral over gamma, or our parametrized version right here, is actually always less than or equal to 0 in the limit as r approaches infinity. And since we figured out the upper bounds for this integral right here, the only way for this thing right here to be less than or equal to 0 is that if it is 0 itself. So this thing right here in the limit as our r approaches infinity is just going to go to 0. So finally we can say that our integral over gamma contributes nothing to our contour. So it's just going to add 0, which is nothing. Alright, so once we've evaluated all of our integrals right here on our contour, we're ready to put everything together. So in the limit as r approaches infinity and epsilon approaches 0, we're going to get this expression right here. And what is this equal to? That's still equal to the value of our contour, which is still 0, because our contour will still be closed over an analytic domain under these limits right here, so it's still going to be the same value. And what can we do right here? Well, notice that this part here is of interest to us because you see this integral right here is exactly this integral right here, which is what we wanted to find out from the very beginning. So let's just muck around with this expression a little bit. We have a minus I pi, so why not move it to the other side? So we're going to get 2i times the integral from 0 to infinity of sine of x over x being equal to I times pi. And notice these i's here will cancel each other out. And we're going to get 2 times the integral from 0 to infinity, but remember from the very start that it's exactly equal to integral from negative infinity to infinity of sine of x over x dx, and of course the dx up here, and that's exactly equal to a pi. And this right here is the final result for our integral today. Alright, so that's pretty much it for this video. Hope you guys enjoyed, and I'll see everyone next time.